Bismillahirrahmanirrahim. In our today's video, we will discuss about the steady state error. Control system analysis and design focus on three specifications. There are transient response, stability, and steady state errors. We started our discussion from the transient response analysis. We discussed first and second order system, and we discussed about different properties of transient response. Next, we will discussed about stability, that if natural response grows without bound at the time as time approaches infinity, the system will be unstable. And if the system is stable, we are now ready to discuss about the steady state error. Steady state error is the difference between input and output for a prescribed test input as time approaches infinity. Like in this closed loop system, we will have any test input and we will see what will be the output. The difference between input and output will be equal to the steady state error, but when time approaches to infinity. We have already discussed about the elevator example. Let's discuss it again. Suppose the user press the fourth floor button, the elevator starts to move to the fourth floor. As the output reaches within 98% of the final value, we can say that the output has reached its steady state value. The difference between output and its input will be steady state error as time approaches to infinity. The most common test inputs that are used in the analysis of steady state error are three, that are step input, ramp input, and the parabola. Step input, as we can see that it is used for a constant position. If we want to find the what will be the error for a value that is constant, so we will give the system a unit step input. The steady state error will tell us that for any constant input what will be the output. Similarly, if value is increasing linearly, or we can say that for a constant velocity we use ramp input, and for constant acceleration we use parabola. Time function of unit step is 1 because of unit step has one value, ramp has finite t value, and parabola t square over 2. The Laplace transform of 1 is 1 over s, t is 1 over s square, and parabola is 1 over s cube. We can assume a position control system to elaborate how these three test inputs are used. This position control system, where the output position follows the input commanded position, the step input represents the constant position and thus useful in determining the ability of control system to position itself with respect to a stationary target, such as a satellite in the geostationary orbit. Similarly, the ramp input represents constant velocity input to a position control system by their linearly increasing amplitude. These waveforms can be used to test a system ability to follow a linearly increasing input, or equivalently to track a constant velocity target. For example, a position control system that tracks a satellite that moves across the sky at a constant angular velocity would be tested with a ramp input to evaluate the steady state error between the satellite's angular position and that of the control system. And finally, the third test input, that is parabola, whose second derivative are constant, represent constant acceleration input to position control system, and it can be used to represent accelerating targets such as missiles to determine the steady state error performance. So let's take an example of unit step input. The output 1 has steady state error equal to 0 because in the steady state condition the difference between output and input is 0. The output 2 has finite steady state error. These steady state error are for the step inputs. Since we are concerned with the difference between the input and output of a feedback control system, our discussion is limited to the stable systems only, where the natural response approaches to 0 as time approaches to infinity. The unstable systems represent loss of control in the steady state and are not acceptable for use at all. The expressions we derive to calculate the steady state error can be applied to that it will be not be applied to unstable system. So we in the whole discussion we will be assuming that all the systems used here are the stable systems. So in our next figure we have shown used ramp test input. The output 1 has 0 steady state error and output 2 has finite steady state error, that is E2, whereas output 3 has infinite error. The system will be stable, but the because we have used all the system, but this is our not this output is of for another system that is not of our concern. So steady state error of closed loop systems. Error is the difference between input and the output of a system. Here we have a general representation of a closed loop system where T of S is a transfer function of the closed loop system. E will be the difference between input R of S and the output C of S. T of S is the closed loop transfer function, and E of S for unity feedback system is shown here, and this is another way to represent the closed loop system, and it is for the unity feedback system. System with finite steady state error for a step input. For now we will discuss that we have a test input that is 1 over S unit step, and we are assuming that K term is a constant and it is a pure gain. So in this example, in this particular example, the error cannot be 0 because this K is a pure gain. If we make the error equal to 0, here this will also be equal to the output will also be equal to 0, but we require a finite output. So E of S cannot be 0. We say this system is a finite steady state error for a step input due to this pure gain. To remove this steady state error, we need a integrator. In this particular system, the steady state error will be equal to 0 if k is a pure gain, no matter, because we have a integrator. The particular calculation will be discussed in next slides. For unit step input, the steady state in the steady state, the C of if C of t equals R of t, error will be equal to 0 because R minus C will be equal to 0. But for a pure gain, the error cannot be 0 if output to be finite and non-zero. So by using integrator, we can make this error equal to 0. Laplace transform theorems that will be used in calculating the steady state error are three. First is integration theorem. The integral will be replaced with the 1 over s final value theorem. At time approaches infinity, the Laplace will be equal to limit s approaches to 0, s and f of s function, and initial value theorem for at time 0, limit s approaches to infinity, s f of s. For first, we have assumed that the all roots are in the left half plane and no more than one can be on the origin. And for the second theorem, we have assumed that f of t must be continuous, or it can have a step discontinuity at the origin and no pulse or derivative at the origin, time equal to 0. Steady state error for unity feedback system. Error will be equal to difference between input and output. R of s minus C of s will be equal to error as shown from the figure, whereas C of s output is multiple of R of s and T of s, transfer function and input. Putting the value of C of s here and taking R of s common, equal to 1 minus T of s. Applying the final value theorem, E of infinity will be equal to time approaches infinity, E of t will give us limit s approaches to 0, s e f e of s, as function here is E of s, as discussed in the previous slide. So steady state error will be equal to limit s approaches to 0, s from here from the formula, and remaining E of s term here. We discuss a particular example for this case. Find the steady state error for system shown in this figure, and transfer function is 5 over s square plus 7s plus 10, and input is unit step. So as unit step input, the R of s will be equal to 1 over s, and transfer function will be equal to 5 over s square plus 7s plus 10. So error will be equal to R of s into 1 minus T of s. Entering the values and taking the R of s is equal to 1 over s, T of s is this term, and taking LCM will give us this term. Now find a steady state error in the time domain. We will apply the final value theorem. Limit s approaches to 0 will make all the s term equal to 0, and we get 5 over 10, which is equal to 1 over 2. So our steady state error for this particular case with unit step input will be equal to 1 over 2. In our today's video, we have discussed about the steady state error, and in our next video we will continue our discussion using how to reduce steady state error with the integrator. Thank you.